James Webb just saw Europa for the first time, and it shouldn't be possible. Right now, while you're reading these words, something is happening that almost nobody on Earth knows about. A world covered in ice, far smaller than our own, locked in orbit around the largest planet in the solar system. It is not a gas giant. It is not a rocky world like Mars. It was built before the first telescope, before radio, before any spacecraft left our atmosphere. Its diameter measures roughly 1,940 miles, a little smaller than Earth's moon. Yet this object sits 390 million miles from the Sun on average. That distance alone makes the discovery we are about to discuss nearly impossible. This finding is forcing scientists to rewrite what we thought we knew about how carbon moves between oceans and surfaces in our solar system. The researchers are not using words like interesting or unexpected. They are using words like astonishing, baffling, and we were wrong about the source. This is the story of Europa, and here is the part the headlines are not telling you. It is not just what the James Webb Space Telescope found on its surface. It is what that carbon dioxide means for the hidden ocean right beneath, an ocean that directly affects any conversation we have about life beyond Earth. It is what is happening to our understanding of this moon right now, in 2026, that nobody is talking about. And it is what is going to happen when future missions reach it, dates already locked into the calendar. Stay with me, because by the time this is over, you will never think about Europa the same way. The story of Europa does not begin with the James Webb Space Telescope. It begins decades earlier, with patient, careful work by scientists, using the tools available at the time. In 1979, the Voyager 2 spacecraft flew past Jupiter and sent back the first clear close-up pictures of Europa. Scientists saw a bright, smooth sphere, marked by long, dark cracks. The surface looked surprisingly young. Most worlds at that distance from the Sun are heavily cratered and ancient. Europa looked different, as if something was actively changing its face. Then, in 1989, NASA launched the Galileo spacecraft. It took 6 years to reach Jupiter, arriving in 1995. For the next several years, Galileo studied the moons of Jupiter. Its magnetometer picked up something unexpected. Europa's magnetic field was behaving in a way that could only be explained by a layer of salty liquid water beneath the ice. This subsurface ocean is estimated to be roughly 60 miles deep in some places. That is deeper than most oceans on Earth. The tidal forces caused by Jupiter's gravity keep the water liquid, even though the surface temperature stays around -260 degrees Fahrenheit. For the next 2 decades, scientists debated what this ocean might contain. One of the biggest questions was carbon. Life as we understand it needs carbon. If the ocean had no accessible carbon, the chances of interesting chemistry dropped sharply. That question stayed open until 2023. The James Webb Space Telescope, with its 6.5-meter primary mirror, observed Europa using its near-infrared spectrograph. A team, including Samantha Trumbo and Michael Brown, studied the data carefully. On September 21, 2023, NASA announced the results. Webb had detected carbon dioxide on the surface of Europa, and the strongest concentrations were in a region called Terra Regio. The evidence pointed to an internal source from the subsurface ocean. This was not an easy observation. Europa is hundreds of millions of miles away. The light is faint. Jupiter is bright and interferes. Yet the telescope succeeded. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. These numbers matter. They remind us of the scale and the difficulty. The 1,940-mile diameter world is small compared to Earth, but its ocean may hold more liquid water than every ocean on our planet combined. The 6.5-meter mirror collected the faint infrared light across that enormous distance. And the 60-mile deep ocean is the hidden part that makes this discovery important. Researchers have been clear. This does not prove life exists. It does show that carbon from the ocean can reach the surface. That connection was missing from earlier models. Many unknowns remain. We do not know exactly how thick the ice is everywhere. We do not know how often material moves upward. We do not know the full chemistry inside the ocean. These honest gaps are part of the science. The discovery came from real, published data. No exaggeration. Just careful measurement. Let us walk through the physics step by step, without hype. Europa orbits Jupiter every 3.55 days. The orbit is not a perfect circle. Because of that slight stretch, Jupiter's gravity pulls harder at some times than others. This creates tidal forces that flex the moon. The flexing creates heat through friction. That heat is enough to keep a large layer of water liquid beneath the ice crust. The ice crust itself is probably 10 to 30 miles thick in most places. Below it lies the ocean. In that ocean, carbon exists in dissolved forms, carbonates and other compounds. In certain regions, the ice shell is disrupted. These are called chaos terrains. Terra Regio is one of them. Here, the surface has broken, shifted, and refrozen many times. Material from below can reach the surface through these zones. Once on the surface, the carbon dioxide freezes and mixes with the water ice. The James Webb Space Telescope detected 4 clear spectral features that match CO2 ice. The strongest signal came from Terra Regio. This is not a sudden explosion of material. It is a slow geological process that has likely been happening for a very long time. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. The 1,940-mile diameter sets the size of the entire world. The 6.5-meter mirror allowed us to see the chemical signature from Earth's vicinity. The roughly 60-mile deep ocean is where the carbon likely originated. Scientists have run computer models of this process. Some models show convection cells in the ice. Others show occasional melting along cracks. All models have uncertainties. The Webb data now helps narrow which models are more likely. The surface of Europa is also bombarded by radiation from Jupiter. This radiation can change molecules over time. Yet the CO2 signature survived well enough to be measured. This observation pushed the limits of what is possible. The distance to Europa is 390 million miles on average. Light travel time is more than half an hour one way. There is no way to fix problems quickly. The James Webb Space Telescope must work perfectly with the instruments it has. Observing time is limited. Every hour spent on Europa means one less hour for distant galaxies. The team had to make the most of short observation windows. The signal is extremely faint. Europa reflects a lot of light, but the specific absorption features from CO2 are subtle. Jupiter's glare makes the measurement even harder. Despite all of this, the data came through clearly enough for 4 separate spectral bands to be identified. Researchers still cannot fully explain every detail of how carbon travels through the ice shell. The process remains difficult to model completely. The challenges of observing Europa cannot be overstated. The Moon is on average 390 million miles from Earth. Depending on where Earth and Jupiter are in their orbits, that distance can stretch to more than 600 million miles. Sunlight at Europa is only about 1/25 as strong as it is here. The infrared signal that Webb needs to detect is incredibly weak by the time it reaches the telescope. The James Webb Space Telescope sits at the second Lagrange point, roughly 1 million miles from Earth. From there, it must point its 6.5-meter mirror with extreme precision. Any small error in tracking would lose the faint signal. Jupiter itself is a massive, bright source of both visible and infrared light right next to Europa in the sky. The telescope's instruments had to carefully subtract that glare. Power is another real limit. Although Webb uses solar power, the arrays receive far less energy so far from the sun. Every observation is scheduled months in advance. There is no second chance if clouds of gas or instrument issues interfere. Despite these constraints, the 2023 observations succeeded. The near-infrared spectrograph collected enough photons in a limited number of hours to identify carbon dioxide. This fact alone shows both the engineering achievement and how difficult future detailed studies will be. Researchers openly state that many questions remain. We still do not know the exact thickness of the ice shell across the entire Moon. We do not know how frequently or how strongly the ocean communicates with the surface. Some models suggest the ice may be only a few miles thick in places. Others suggest it is much thicker. The Webb data supports exchange, but does not settle the debate. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. These 3 numbers keep returning because they define the entire challenge. The small 1,940-mile world holds an enormous hidden ocean. The 6.5-meter mirror is what let us see the carbon signature from such a distance. And the 60-mile deep ocean is the reservoir we are trying to understand. The first clear finding from the Webb data is the location of the carbon dioxide. It is not spread evenly across Europa's surface. The highest concentrations appear in Terra Regio, a region of chaos terrain. Chaos terrain is geologically young. The ice here has been broken into blocks, tilted, and refrozen in a messy pattern. It looks like a jumbled puzzle. On a world only 1,940 miles across, Terra Regio covers an area that would be comparable to a medium-sized U.S. state or a large portion of Alaska. Within this zone, the carbon dioxide signal is strongest. This distribution strongly suggests the carbon came from inside the moon rather than from outside. Meteorites and cosmic dust should leave a more uniform coating. The concentration in one young region points to material rising from the subsurface ocean. A plain language translation: the ocean is not completely cut off from the surface. In at least some places, its chemistry is leaking upward. Relatable comparison: imagine a frozen lake on Earth, where chemicals from the deep water below rise and concentrate exactly where the ice has cracked and turned over recently. That is the picture emerging on Europa. What remains unexplained? Exactly how the material travels through miles of ice. Does it happen through narrow cracks? Through slow convection? During occasional melting events? The models still disagree. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. This single finding changes the conversation. Earlier models often treated the ice shell as a thick, permanent barrier. The Webb data shows that barrier is at least partially permeable in geologically active zones. The second major finding concerns the chemical form of the carbon. Webb detected 4 distinct absorption features in the infrared spectrum. These match laboratory samples of carbon dioxide ice, mixed with water ice and other compounds. One particularly clear band appears near 2.7 microns. This is not loose gas, it is frozen CO2 incorporated into the surface ice. The way it is mixed tells scientists it most likely arrived in liquid form from below and then froze in place. Scale comparison: from nearly 400 million miles away, the telescope identified a substance that, if you were standing on the surface, might appear as only a thin, sparse layer, yet that layer carries the chemical fingerprint of the hidden ocean. Unexplained details: how long this carbon has been reaching the surface, and whether radiation from Jupiter changes its form over time. Jupiter's powerful magnetic field traps particles that rain down on Europa, creating one of the harshest radiation environments in the solar system. This radiation can break molecules apart or create new ones. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. The presence of these specific spectral bands gives confidence in the detection. It is not a single weak signal. Multiple independent features line up with CO2. This tells us the exchange is not just theoretical. It has left measurable evidence on the surface. The third finding is more cautious. Webb did not detect strong signs of active water plumes during its observation period. Earlier Hubble Space Telescope images had suggested possible plumes of water vapor erupting from Europa's south pole in some years. The absence of clear plume activity in the Webb data does not mean plumes never happen. It means they may be rare, small, or simply not active when the telescope was looking. The carbon dioxide may instead reach the surface through slower processes in chaos terrain rather than dramatic eruptions. Comparison: like groundwater slowly seeping to the surface on Earth, instead of shooting out as a geyser. Both can connect the deep water to the surface, but one is quieter and steadier. Researchers remain open on this point. Future missions will search for plumes more systematically. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. The lack of strong plume detection during the Webb observations does not close the book on activity. It simply narrows the possibilities. Plumes, if they exist, may be intermittent, appearing only during certain tidal stresses or in specific locations. The carbon dioxide found in Terra Regio suggests that material transport can happen even without large, visible eruptions. This slower exchange is perhaps more important over long periods. A steady trickle of ocean chemistry reaching the surface could allow reactions with sunlight and radiation that would not occur in the dark ocean below. What remains unexplained is the full plumbing system inside the ice shell. How many pathways exist? How wide or temporary are they? Models range widely, and current data cannot yet decide between them. Researchers continue to run simulations, but they acknowledge the limitations of working from such a great distance. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. These numbers ground every discussion. The entire world is only 1,940 miles across, yet it hides an ocean that may be 60 miles deep. The 6.5-meter mirror is what gave us our clearest chemical look so far. The fourth and perhaps most significant finding concerns what this means for habitability. Carbon is a fundamental requirement for the complex molecules that life depends on. The confirmation of an internal carbon source means the subsurface ocean has had access to this key element for billions of years. Combined with liquid water and the constant energy from tidal heating, the basic ingredients are present. The ocean likely sits on top of a rocky seafloor. There, interactions between water and rock could release additional minerals and chemical energy, similar to hydrothermal vents on Earth's ocean floor. These vents are places where life thrives without sunlight. A plain language translation: the ocean is not just water. It appears to be a chemically active environment with carbon available. Relatable comparison: think of Earth's deep oceans, where life exists around vents that use chemical energy instead of sunlight. Europa may have similar conditions, but on a much larger scale. This does not mean life is present. Many steps remain between simple chemistry and living organisms. The radiation environment on the surface is deadly, and the ice shell is thick. But the Webb discovery removes one major objection that existed before 2023. Honest unknowns are still large. We do not know the temperature, pressure, or exact salt content of the ocean. We do not know if phosphorus, nitrogen, or other essential elements are abundant. We do not know if the chemistry has ever crossed the threshold into prebiotic molecules. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. These facts repeat because they define both the promise and the difficulty. A small world with a huge hidden ocean, studied through a powerful but distant mirror. The four findings together: location in terra regio, chemical form, limited plume evidence, and habitability implications, build a consistent but incomplete picture. The ocean and surface are connected. The connection is real, but its details remain partly hidden. So where does the story go from here? The Europa Clipper mission, launched in the mid-2020s, is currently on its way to Jupiter. It is expected to arrive in the early 2030s. Once there, it will conduct dozens of close flybys of Europa. Its instruments are designed to map the ice shell thickness, measure magnetic fields, search for plumes, and analyze surface chemistry in far greater detail than Webb could from a distance. Clipper is not a lander. It will not drill through the ice, but it will give us global maps and repeated observations over several years. This should answer many of the questions left open by the 2023 Webb data. After Clipper, concepts for future missions are already being discussed. Some propose orbiters with ice-penetrating radar. Others talk about landers that could sample surface material directly, or even small drills. These ideas have timelines stretching into the late 2030s and 2040s. Dates are not fixed yet, but planning is active. Even when Clipper finishes its work, Europa itself will continue its quiet activity. The tidal heating will not stop. The ocean will remain. The slow exchange between depths and surface will likely continue for billions of years more. There is nothing to stop it. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. These numbers will still apply long after our current missions end. The world is small. The mirror that first gave us this clear carbon view was 6.5 meters across. The ocean below may be 60 miles deep. Future missions will build on this foundation. Scientists are careful in their projections. They do not promise discoveries of life. They talk about better data, better maps, and clearer understanding of the chemistry. That measured approach is what makes the findings trustworthy. So what does all of this actually add up to? One small icy world, 1,940 miles in diameter, holding a vast ocean, possibly 60 miles deep, studied from afar by a telescope with a 6.5-meter mirror. The detection of carbon dioxide in terra regio is not flashy proof of extraterrestrial life. It is quiet, precise evidence that the hidden ocean is chemically linked to the surface we can see. This link matters for any serious discussion about habitability in our solar system. It shows that even in cold, distant places, chemistry can connect deep water to the outside world. It is genuinely worth wondering what else might be hiding beneath the ice of Europa, and beneath the surfaces of the many other worlds we have only begun to examine. So what does all of this actually add up to? One small icy world, 1,940 miles in diameter, holding a vast ocean, possibly 60 miles deep, studied from afar by a telescope with a 6.5-meter mirror. The detection of carbon dioxide in Terra Regio is not flashy proof of extraterrestrial life. It is quiet, precise evidence that the hidden ocean is chemically linked to the surface we can see. This link matters for any serious discussion about habitability in our solar system. It shows that even in cold, distant places, chemistry can connect deep water to the outside world. It is genuinely worth wondering what else might be hiding beneath the ice of Europa and beneath the surfaces of the many other worlds we have only begun to examine. The James Webb Space Telescope gave us one important piece in 2023. Future missions like Europa Clipper will add many more in the 2030s. Each new data point will be hard-won, limited by distance, power, and the harsh environment around Jupiter. Yet the work continues because the questions are fundamental. Does life need sunlight? How common are subsurface oceans? Can carbon and water and energy come together in places we once thought too cold or too far? Europa is one of the best places in our solar system to test these ideas. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean. These numbers have appeared again and again throughout this story. They are not dramatic, they are simple facts. But together, they describe a world that continues to surprise us. A small moon with a deep hidden ocean. A powerful telescope that reached across hundreds of millions of miles to find carbon. An ocean whose chemistry we are only beginning to understand. When Clipper and later missions eventually send their last signals, Europa will not stop. The tides will keep flexing the interior. The ice will keep cracking and shifting in places. The slow exchange between ocean and surface will continue. The moon has been doing this for billions of years, and will keep doing it long after our current generation of scientists and engineers is gone. This is the part the headlines often miss. The real story is not about sudden breakthroughs or immediate answers. It is about steady, careful work over decades. It is about respecting the enormous distances and difficulties instead of pretending they do not exist. It is about stating clearly what we know, what we do not know, and what we might learn next. You will never think about Europa the same way again. A small, icy world that should be frozen and dead is instead active, chemically connected, and still full of honest unknowns. It is one of the most compelling places in our solar system to keep searching. If this kind of careful, fact-based look at space discoveries is useful to you, please subscribe and turn on notifications. This channel exists to walk through real published research without exaggeration or hype. New findings are coming in the years ahead, and we will break them down the same way, calmly, precisely, and with respect for what remains unknown. Thank you for staying with me through the full story. 1,940-mile diameter, 6.5-meter mirror, roughly 60-mile deep ocean, one small world, one powerful telescope, one hidden ocean still waiting to be understood.